Okay, we'll start the session now. If you recall, in our last session, we discussed linked list and the modified version of linear linked list is circular linked list. So today we shall see how to build a circular linked list. The logic is little different because there should be a loop forming. That is, the last node should point back to the first node. So in my previous session, I showed you that if you have a circular linked list, so the head node will be here and the other nodes will be linked together and the last node will point back to the first node. Okay. So if I have to construct such a linked list, then what all operations I have to do? Or how should I go about building the linked list using add node or append node operations? And if whenever you have to delete, what happens, and when you want to display, how you display the contents of the linked list. Now, initially, the head is pointing to null, and when you want to add a new node, all that you have to do is create a new node, store x in that, or whatever x value that is passed, and if head node is equal to null or null pointer, then you just have to say head equal to new node, isn't it? So this is only the first part. In a linear linked list, we would just do this and close. But in circular linked list, after you have made head point to the new node, that is, you are now making this head point to the new node, right? And the next of this new node should point back to the node itself. So here, new node arrow next should be equal to head. Now, as a result, what happens? This which is pointing to null will now point back to the same node. So we have a circular linked list even when there is only one node. This part is clear? Okay.
Yes, sir.
Now,
Yes.
what if there is one node or more than one node? And now if I want to add, that is, we go to the else part. That head is not pointing to null. It is pointing to at least one node. In that case, if I were to add a new node, how would I proceed? Okay. So let's say this is the initial scenario. That is, you have only one node here. Now, in the else part, again, there will be a new node created. And let's say the value is y here. And the next is pointing to null. So here, if I want to add this new node and make it part of this linked list, and add node, we know it is going to be added at the beginning of the list, isn't it? So first thing that I would do is new node arrow next will be head. In the else part, new node arrow next will be head. So what happens in the diagram? This will point to, okay, and this now this link which is here. Now remember, this node will be the last node in the linked list, right? So before we set head here, what should happen? Head arrow. In fact, this is the only node in the linked list. So you can use head arrow next, make it point to new node. but that is not what is going to work. Okay, so what you have to do is you have to take one temporary uh, pointer and traverse it till you reach the last node in the linked list. So how to do that? While t arrow next not equal to head, t arrow head not equal to head, t equal to t arrow next. So in this case, t will start here. T arrow next itself is head, so it will come out. Okay, so what I can do now is use this pointer t arrow next is equal to noon, and head should now point to noon. Now, what all happens when I do these two steps is that this head will now point to new node here. Okay, and this pointer will point to, you can take it this way or whichever way you want, it will point here. So as you can see, again we have a circular linked list with head pointing to the beginning of the list, right? So this logic will always work even when we have one node or more than one node, right? Now, why we have to do this step is that in this case, when we have two nodes, you have to start from here, right? T equal to this head node. You have to traverse till you reach the last node, which is this one. And when we add a new node, the pointers have to be altered like this. Only then you will have a circular linked list. Okay. Now, how do I display this linked list? So that is again, you take a pointer t which is pointing to head, while t not equal to head. Okay. Now the problem is t is already head. So how will you proceed? So what you can do is first print uh, the value in the head node and then enter the loop. So here cout head arrow data, and then t equal to t head arrow next. Okay, so this has to be done here, and then within the body of this, if t is not equal to head, then you cout t arrow data and t equal to t arrow next, so that everything in the linked list is displayed. Okay, so in our linear linked list, we were taking t till the end, t not equal to null pointer, we are doing this. But now there is no null pointer at the end of the linked list. All of you agree? You have to traverse t until you reach the last node. How do I
Yes.
know? How do I know it is last node?
Last one.
When t becomes head again. All right. Okay. So let's see whether this works
Yeah.
fine
Yes.
when I create a circular linked list. So the node definition remains the same. You have data part and next pointer, and in the constructor I'm initializing this, and there is a head pointer which is initially null. So in the constructor of this circular linked list, you just have to make head point to null. And let's see how we can do this add node first. We'll be receiving a value So first thing is create a new node tar node equals to so this will create a new node and initialize the data to X. Okay. Now we'll check first if head equal to null pointer. So initially that is the case. Then what will we do? You will make head point to the new node and head arrow next, or you can use new node arrow next equal to head and then return from here. The else part, you can put else or you can just proceed because it will not go to else if it is done if it has entered the if block. So here, what is the scenario? There are nodes in the linked list. So what you do is you take a temporary pointer which is pointing to the head. What are the steps we did? The else part, t arrow next equal not equal to null. So that is what you should do. While t arrow next not equal to null pointer, you do t equal to t arrow next. It means go till the last node. Okay. So once you are at the last node, t will stop, and now you should make this new node arrow next should be equal to head, isn't it? The new node should point to head, and head should be made to point to new node, and t arrow next should point to the head. These are the three steps. Okay. So the insertion will be complete when you do these three steps in the later part of the code, when there is at least one node present in the linked list. Now let's see whether this displays the linked list correctly. Here you will take a temporary node RT, make it point to head, arrow next. Before you enter the loop, you print the first node value, head arrow data, while t arrow next, while t arrow next not equal to head. See out t arrow data t equal to t arrow next. Okay. So adding node in circular linked list is slightly involved, and display one changes you have to start with t equal to head arrow next and display the first value and then proceed till you reach the last node and keep displaying it. So let's see whether you get the circular linked list. cl dot add node 7, cl dot add node 3, cl dot add node and cl dot display. So let's see whether we get the required output. What happened? I think so. Nothing is coming on the screen. Made some mistake somewhere. Initially head is null pointer. If it is null pointer, head equal to new node next equal to head return. Okay, so first node is added. T arrow next not equal to null pointer, T equal to next. Okay. New node arrow next equal to head. Head equal to new node, T arrow next equal to last node will point back to this. Display T. It seems to be correct. No? Let's see. Some error it is showing. Permission denied. Just a minute, I'll just see the version which I've implemented here. It is the same thing. Head is null pointer. Head equal this. There is one extra pointer I've taken that you can ignore. So here, what I'm doing is I am adding node 8, 4, and 2 and displaying it. So append part we shall see later. Let me check whether this is working fine. I have installed McAfee antivirus. Maybe that is causing some problem or not. Quickly implement this uh, and see whether we are getting the output because it should come without any issue. Again, same thing is coming. Permission not denied. One of you just try. Let's see whether it is problem with my machine here or because today I updated this McAfee antivirus that might have put some restrictions on the execution.
Yes, sir. Try.
This is a compiler. Now, if I try this circular linked list and try to run, it will execute perfectly. As you can see, circular linked list is showing 537 as the output. Right. So we have seen how circular linked list can be implemented. Now, one other important application of linked list is linked stack. Now, how would I implement that? So I define a node with data and the next pointer, initialize them accordingly. Only changes, then node will have to node constructor will have two arguments instead of one, the value x and the node next node pointer star. This will make the logic implementation very, very simple. In the constructor of linked stack, all that I do is initialize the top to null and proceed further. So in the public section of this, I'll write a constructor linked stack null pointer. And we have to implement push, then pop, pop will take in arguments and display. So let's see how we can do all these three one by one. So push operation, you will need to pass a value here, index. All that I have to do is just call the push operation. I have to create a new node by passing top as the argument and the value x. And the result, you can just store it in top. So this will ensure that the node is appended at the beginning of the list and the pointer is returned back to top. You can wait into three steps, but that one step you can do the push operation. You see how easy it is to implement a push operation in linked stack. And most important, you don't have to check whether the stack is full or not. Because the dynamic stack is goes on allocating space on the heap. And you're not going to use way too much memory. Maybe 10, 15 elements you will push, and that is quite accountable in today's computer systems. Now, the pop operation when you want to perform, you have to check whether the stack is empty. So if top equal to the pointer, you have to see out stack empty and return -1. If it doesn't get into this circuit block, there are some elements to be popped. So first you pick up the data on the top using top arrow data, and then you take a temporary pointer top equal to top. I'll tell you why this is required. Make top equal to top arrow, negative, so that it points to the next element. No, we have to delete the pointer because whenever the located space is retained, so that is why we require a temporary pointer. You cannot say delete top. Say delete top, all objects pointed to by the top pointer will be deleted. You want to delete only one more, the one which is deleted. Okay, and here you can return x. And in display, you take again a pointer pointing to the top, while t is not equal to null pointer. You see out the arrow data. Display back one values one below the other, and you just say t equal to t arrow. Next, I think all these two instruction must be in the block. So that is what it display. Let's see whether our stack functions correctly. So I say link stack ls dot push 8 ls dot push 9 ls dot push 3 and then ls dot display. So let's see whether all these three values will be. You can see on the stack you have 398 because 3 is the last push last stack coming in the block. Okay. Similarly, you can check whether the pop is happening or not. So you can just say see out pop element is, you can give a slash n and you will say pop. And this has to be output. What is on the top now is 3, and 3 should be popped as a consequence. So let's see whether that's happening. This is compiler is taking a little longer time than usual. That may be because of the McAfee that is installed. So 398 and element pop is 3. And after this, if you display stack, you will get only 998. So linked stack can be easily implemented. This is one important application of linked list. Okay. Yeah. Now, binary tree. We need to understand what a binary tree is. So, linked list is a linear data structure where nodes are linked to one another in a linear fashion. Whereas in a binary tree, every node will have two branches. One is left, the other one is right. Unlike linked list where you have only one pointer which is next. Okay. So each node will contain a data part and two pointers left and right. Now here is an example of a binary tree where node 7 is pointing to 3 and 9. On the left you have 3, on the right you have 9. Similarly, node 3 is the parent of the two nodes 6 and 5. 6 is on the left and 5 is on the right. Okay. And the first node in the binary tree is called as root node. Alright. And every tree will have a depth. That is, how far is the leaf node from the root. So in this case, the leaf nodes are 6, 8, 5 and 8. And they are 3 distance away from the root. So the depth of the tree is 3. Okay. And any tree which contains all the nodes of the binary tree with no gaps in between is called as a complete binary tree. It means if I number the nodes from 1, 2, 3, from top to bottom, left to right, no numbers should be missed. So in this case, 1, 2, 3, 4, 5, 6 is there. So no number is missed when I count from 1 to 6. So it is a complete binary tree. And almost complete binary tree is one which is missing one or two nodes in between. Like here, node number 7 is missing. So remember one thing, the relation between depth and number of nodes of the tree. So if the depth is 3, 2 to the power n minus 1 is the formula, and you will see exactly 7 nodes have to be there. So if this binary tree has to be complete, there should be 7 nodes, but 1 is missing. So that's why it is almost complete binary tree. Now, why it becomes important to have a tree which is balanced is that suppose you have a linked list with all nodes on its left, as in this case. So it's called a skewed binary tree where every node is pointing to a left node until the end. So there are no nodes on the right hand side. Because of this, this skewed binary tree will be like a linked list. So you will lose the advantage of being a binary tree and acting like a linked list. So to get it balanced, that is have almost equal number of nodes on either side of the root or every node in the binary tree, we need to balance it out. The way to balance it out is to rotate the binary tree around some element, like around 5. If you rotate 7, you get this binary tree. Now balancing the tree will have important advantages that elements are equally spaced placed on either side of the tree and the search becomes faster. Now how do I create a binary tree? We have to define a class node, uh, and you should have three data members. First one is the integer type. The second two are of type node only, and they are pointers, node star left and node star right. And in the constructor of this class, we have to initialize the three data members. That is, data should be initialized to x and left right should be initialized to null pointers. So if whenever you create a new node, it will contain x and two pointers left and right pointing to null initially. So when you want to create a binary tree, you create one more class binary with node having a pointer named root of type node star. And in the constructor of this, you initialize root to null pointer. So if root is null, new node should be made to point to root, and left right is anyway null. So first node will be created. If you want to put a node on the left, then you check whether value of x is greater than y. If so, put it on the left, otherwise put it on the right. So if you follow this logic, you'll have a binary search tree. Uh, we shall see the implementation, how binary search tree will be created. Every node will have a value which is greater than all the values on its left, and all values on the right will be greater than the parent node. So if you follow this logic, we'll end up getting a binary search tree whose search time will be log n. So in our next session, we shall see how to create a binary tree and perform the operations like traversals. There are three traversals here: in order, pre-order, and post-order. If you traverse a binary tree in order, you'll get a sorted list. And searching will be pretty fast because elements are so arranged that irrespective of how many elements we have, it will take at the most log n time. That is, if you have 32 elements, log 32 is 5, and you'll get the search done at most 5 comparisons. That's the advantage. So in our next session, we shall see the implementation of binary tree. Until then, thank you and bye for now.